Now, in this question, we want to calculate the amount of work energy that's either going to be gained or lost by a system whenever a gas expands from 20 liters to 35 liters against a constant external pressure of 2 atm. And what we can do is we can make a picture of what's going on in this question to get a better idea of how all these numbers fit together. And what I'm going to do is I'm going to make a container like this, and I'm going to put a lid on the container, and this lid right here can either expand or can shrink. And what I'm going to do is I'm going to put some gas molecules inside of this container, and I'm going to put some gas molecules like right here, and then an arrow to show its direction, and then I have a gas molecule right here, and then there's an arrow to show its direction. And this is the internal pressure in here. And there's also going to be an external pressure that I'm going to put over here. So we can have some gas molecules over here going around the container like this, and maybe a gas molecules right here, and it's going and hitting the container kind of like this. And so there's going to be a difference in pressure between the internal pressure and the external pressure. And in the question, it says that the external pressure is going to be 2 atm. So the pressure of the external part of the container is equal to 2 atm. So that's the external pressure. And the internal pressure is going to be right here. So we have the pressure, and I'll put I in for internal, and that's going to be some number greater than 2. So I'm just going to put it's greater than 2 atm. And the reason why I know it's greater than 2 is because this container right here, this lid of the container, is going to expand. It's going to get larger. So it must go from a high pressure to a low pressure. So it's going to go in this direction, kind of like this. And whenever it does that, it pushes against this lid right here. And anytime you have an object that's going to move some amount of distance or displacement, it means work is going to be done. And so what I'm going to do is I'm going to calculate the amount of work using this equation right here. I'm going to say that the work is going to be equal to the negative pressure of the external part of it times the change in the volume. And what you want to do is you want to make sure that this pressure right here is the external pressure, not the internal pressure, because the internal pressure is going to change. And the reason why the internal pressure changes is because as this volume right here gets larger, the pressure goes down. And so if the pressure in here is, let's say, 3 atms, after this pressure decreases because the volume expands, it'll equal this external pressure, and it will decrease until it gets to this pressure here. And in that case, the pressure is both equalized on the outside and the inside. And so this pressure is always changing, so you don't want to use that one. Instead, you'll just use this one right here. And the reason why I want to do a negative right here is because this pressure here, the external pressure, this pressure is pushing down on the container like this. And what we'll do is, to take into account this down direction, is we put in a negative sign. And so what I'll do is I'm going to say that the work is going to be equal to negative the external pressure, which is going to be 2 atm. So I'm going to put a 2 here. And then the change in the volume, we're going to go from the final, which is 35. And so I'll put 35 down. And then we're going to subtract the initial, which is 20. And so we have a 20 here. And then when we do this calculation out, we're going to get the work is equal to negative 2 times, and we got 35 minus 20, so we're going to get 15. And so we'll have work equals negative 2 times 15. We have this negative sign here. That's going to be negative 30. And then the units are, this is atmospheres and this is liters. So this will be atmospheric liters, which is a form of energy. But if you look at our answer choices are all in kilojoules. Now they give us this conversion factor right here. So what I'm going to do is I'm going to convert this number here to joules, because it gives me joules right here. And what I'll do is I'm going to take this negative 30 atmospheric liters like this, and I'll put that over 1 like this. And then what I'm going to do is I'm going to put the atmospheric liters on the bottom, and then I'm going to put the joules up top. And the reason why I put the atmospheric liters on the bottom is so that it can be canceled with this and this. And for the numbers that go in here, I'm going to look right here. There's a 1 right there. So I'm going to put a 1 right here. And there's a 101 for the joules. So I'm going to put a 101 here for those joules. And then when I multiply this number times 101, I'm going to get negative 3030, and that's going to be in joules. And so now that I'm in joules right here, what I need to do is I need to go to kilojoules. So I'm going to take this negative 3030 joules here, and I'll put that over 1 like this. And then what I'll do is I'm going to put the kilojoules up top, and I'll put joules on the bottom. And then I know that for every 1 kilojoule, that's going to be equal to 1,000 joules. And so just like this atmospheric liters cancel with that atmospheric liters, this joules there will cancel with that joules there. And then I'm going to get negative 3.03, and that will be in kilojoules. And so the answer to this question is going to be B right here.